Welcome to Computer Science 226, lecture number 4. This is where we left off last time. We were talking about these, and the next slide that we didn't quite get to is a summary of these things that we were talking about. De Morgan's laws for quantifiers. And what we said is you can take this knot and distribute it across the quantifiers, and you can also do it across ors and ands, of course. But for quantifiers, if you've got a knot and you distribute it across a for-all, it becomes there exists. The knot just kind of continues on, down the line the same way as De Morgan's laws for and or and so forth. And again, there's 4 things. If you just know the first one, I mean, it's all the same. If the knot goes this way, again, it turns there exists into a for-all, and the knot just keeps going out. I mean, all of these things are really the same. This one looks a little bit different, but all they've done is they've just distributed the knot that's right here in front of the predicate, and so when it comes out, it flips that to a for-all, and you would have a double knot, so you get rid of it. All right, but again, like I said, if you just know that first one, the other 4 are kind of derived from that. Okay, so continuing on, we only got 2 slides left, and we're going to do some examples. We talked about some greyhounds last time. Derived, there are no slow greyhounds from all greyhounds are fast. This uses those De Morgan's laws for quantifiers. So we've got g of x means that x is a greyhound. F of x means x is fast. All greyhounds are fast would be for all x. G of x implies f of x. And from there we can, let's see, what can we do? We can break down the implication. So for all x, not g of x or f of x. We can then use one of those things on the previous slide. This is the one that I was talked about last time, where it wasn't not really. I can't draw it. There we go. Nope. Okay, it's still not letting me do it. Let me get it. Let me just get this done. Again, this is technically equal to, again, it doesn't, you normally don't need to do this, but you can. I can put a double knot in front of it. Okay, and then if I chose to distribute that knot, that's in front of whatever's left. So these 2 things are equal. Again, it's really just deriving. You've got this. You put some knots out there. Like I said, you don't necessarily need to memorize all 4 of them. Just know that you can do this. And when you distribute a knot across one of the quantifiers, it flips to the other one, and the knot just kind of continues on down the line. That's what they did in this example. So they double knotted the for-all. They distributed one knot, and we're left with. It is not the case that there exists, and it is not the case. What's in parentheses there? And that's just De Morgan's laws of quantifiers. We then distributed this knot across what's in parentheses, and that's just De Morgan's law for propositions. And so the knot G became G of x, the or flipped to and f of x became not f of x. So we end up with something that looks like, well, I'll read it and then I'll read what we got there. So it is not the case that there exists something that is a greyhound and is not fast. That's really what we were trying to get to. So it is false that there exists something that is both a greyhound and not fast, which is equivalent to no greyhounds are slow, which is what we were trying to prove. We really should have probably quantified what we were trying to get to, so that when we actually got there, that we knew. But again, it's just showing some examples of how to use De Morgan's quantifiers. or De Morgan's laws for quantifiers. And now I'm stuck in, there we go. Okay, brings us to an in-class exercise. All right, so again, we're not proving anything here. We're just coming up with expressions. Express: no intelligent student watches HGTV using the universal quantifier. Previously, we did it using the existential quantifier. This was that answer. Now just do it with, basically all this is asking you to do is to distribute that knot. So take 30 seconds and try to distribute this knot across the quantifier and also across what's in parentheses, the propositions that are in the parentheses. Have a second time. All right, we're ready. Let's see if I can. That is. Let me see if that lets me write on here. Yeah, still not letting me write. What am I missing here? Let's see. There's the pen. Fitness, that's good. Okay. Okay, now we go. Can't erase the way I could do. Okay, so we distribute this knot, okay, across the there exists, and we get for all x. It's not the case I of x and h of x. Okay. Now, technically, I guess you could say that you're done at that point because it did. The problem did just say express it using the universal quantifier, which I've done there for all x. But let's distribute the knot. Let's keep going here. So if we distribute the knot across an and, the and becomes an or, and the signs or the knots on the propositions flips. So for all x, is not the case I of x, and becomes or. It's not the case h of x. All right, again, at that point, you could probably say you're done, but this also fits something else that we talked about called the definition of implication. So we could go so far as to make this into an implication for all x. That would be I of x implies not h of x. Right, which is probably closer to what we were trying to do. No intelligent student watches HGTV. For all x, being intelligent implies that person does not watch HGTV. But really, the way the question was worded, any three of these would be fine because technically, even at that point, we had used the universal quantifier. All right, questions on that? All right, see if you can do this one. Oh, let me have the light on so I can see where it goes. There we go. All right, using De Morgan's law, distribute the knot. So really the same thing we sort of did there before, just all we want to do is just distribute this knot across what we've got there. So take 1 minute and do that, and then I'll do it and reveal the answer, and hopefully they should match. All right, hopefully this wasn't too hard for you. Remember, just there is becomes for all, and the not just kind of continues on down the line. So, I mean, there's two ways to do this. I mean, once you get good at doing these, you should just be able to write it directly. I mean, if I distribute this not, I mean, I realize it's going to stop at the predicate there. I'm going to flip the sign of whatever operators I got, and then it would go across these. And that would be it. You could keep the parentheses there if you wanted to. Make sure that matches my answer. Sure enough, it does. But again, if you're doing it one step at a time, which when you're learning, not a bad idea. Why don't we do that? So, and again, I don't know how did you do it? Did anybody sort of take the approach where I'm going to put the not in front of each group, or did you just sort of send it through the parentheses? Yeah, either one is fine. That's what I would do too. So if we just kind of let this not travel across the whole thing, we first would get for all x. I mean, this way turns out to be a lot of writing, but that's kind of how you do it. Gotta make sure I keep these x's and y's. All right, so that was the not going from here to there. We continue on.
But what about the other not?
What other not?
Besides Q.
Well, see, this is the answer. So we did it just by sort of like inspection. Now we're letting the not travel all the way through. We're going to end up with what's circled there as well. And the way I'm going to do this is kind of like a waterfall thing. So I distribute that not across the for all. So that becomes there exists a y. And then as long as you realize that not had to apply to everything, you're okay. It then needs to apply to this and then it then needs to apply to this other side. So that would be there exists an x. And this is going to become there's an x, not q of x. All right, then if we put all that stuff back together, we get x, this y, not that p of x comma y, or again, however you're most comfortable doing that. I think most people probably just sort of do it in their head, like each one. So that's going to be a for all. Then I know the not's next to the for all and so forth. But however you do it is fine. Just know that this not has to apply to each group of items. So it applies to the first part, the and the second part. All right, any questions on that? Pretty easy. All right, let's see if I got another one.
What's De Morgan's? I'm sorry.
What's De Morgan's?
Yeah, for the all. I'm a bit late again.
De Morgan's for all. You mean so? This the slide. This slide is basically what we're working from. We went over this yesterday, but this is just in a compact table. And again, really, as long as you know the first one, you can derive the rest of them from that. So as long as you know when you distribute the not over a for all, it becomes a there exists, and when you distribute it over there exists, it becomes a for all. You're fine. All right, let's see. I got some more. Got some more here. Oh, let's see how I can. Okay, so the assignment here is to take what's given and translate this statement into English. So C of x is a comedian. I don't know why I put that in single quotes, but I'm just going to quote there. X is a comedian. F of x is funny. the universe is all people. So translate, for all x, C of x implies f of x. So what does that mean?
For all people, being a comedian implies that you're funny.
Okay, yes. Now, give me a less robotic answer. Like, how you would talk to somebody. What would you say?
If you're a comedian, you must be funny.
Right. Or all comedians are funny.
Yeah.
All comedians are funny, right? Nothing wrong with saying it the way you did. We're just trying to, in this case, we're trying to translate them to some English statements that we might actually say. And it's probably easier to do that, like come up with sort of like the robotic answer and then say, well, okay, what is this really saying in English? All right, what about this one? For all x, C of x and f of x.
All people are both comedians and funny.
Right. Everybody's a comedian and they're funny. All people are comedians and they are funny. Yep. All right. Well, here's an interesting one. This is that thing that I said that you probably will never see. There exists an x such that C of x implies f of x.
There exists a comedian, or
There exists at least one comedian that's funny.
So these are from a book somewhere, and I took the answer. So yeah, this is a hard one to express. One way to express it would be someone is a comedian, and that means that they are funny. Like I said, so this has a meaning in English. It almost never represents what you're trying to do in a proof, though, because even though the statement is coherent English, it doesn't really make any sense. So there's someone is a comedian, and that fact means that they're funny. And when I say someone, I mean like some particular person is a comedian, and that means that they are funny. It's just strange, yeah.
are you gonna give a question like that?
Oh no. I will not give a question like that. On the test. Here we go. This one makes a lot more sense. There exists an x such that C of x and f of x. Normally, and the reason I gave this, normally when you write that,
There's a comedian that's funny.
you mean that. Yeah. Somebody's a comedian and they're funny. There is someone who is a funny comedian. Any of those works. 9 times out of 10, I say that because somebody will call me on one, but every time I've ever had somebody write this, they mean this. Somehow in their head it sounds like that's what they're trying to say, but it's really this. Because this statement really doesn't make a lot of sense. Just one person implying something. All right, let's see. Let's see if the next one is. Oh yeah, we went over this. Like I said, I think I got the numbers on all of my other ones correct. It was just that section 1.3 that I had some problems with. All right, so L, x, comma, y is the statement that x loves y. So the domain of x and y is all people. Use quantifiers to express there is somebody whom everybody loves. And you might have to think about that for a second or two. Remember, you've got two variables here, so you're probably going to have two quantifiers. One's going to, in this case, one is probably a there is, and one is probably a for all. And remember, order of those things matter.
There's a y. Everybody x.
Uh-oh.
Or no, there's a.
I'm not the only one seeing that black thing, right? I'm not like blacking out for a second.
There's an x. There's a y that everybody or every x loves.
So that for all x, L. Let's see. There is a y. Y is something. So there is an x that for all x, everybody loves y. That looks right to me. Sure enough, it matches the answer. Yeah. So what would the opposite be? Let's say that we had written for all x there exists a y. hate X and Y. Okay. So that is saying what? That is saying,
Everybody loves a person.
yeah, there's, for all X, everybody in the world, there is, well, for all X, there is someone that they love. But yeah, what we have here is correct. There exists a Y such that for everybody in the world, they love that person. So everybody loves one person. This is kind of saying that for everybody in the world, you can pick a Y that they love. All right, what about the next one? There is somebody whom Lydia does not love. So Lydia's obviously got to go with X, right? And this other person is the Y, because that's the person that she does not love.
There exists a Y, not Lydia, or not that.
Think of it like how it would be. There exists a Y that does not, and then love, and then Lydia, and then Y. Since it's not like a group of people, it's just some person.
Like that?
Yeah.
With a non.
Oh, yes, does not love. And yes, I was going to say, that looks like the right answer. Yes. Yeah, what we did here is we stopped talking about everybody in both of our statements. This one was quantified. It's Lydia. It's just one person, so it's Lydia. So for X, we have Lydia. And that also means that we don't have a quantifier for X, because we've chosen one. So it's not that there exists one, because that's kind of random. That means we can pick one from a bunch of people, and it's not for all. We've quantified that person as Lydia. So there's no statement with X in it. So yeah, there exists someone that it is not the case that Lydia loves that person. Right. All right, let's see. Okay, the next one is the next one we got to go over a few more things for. I thought I had one. I think we might have done that one last time. But yeah, this is the next one is one that I had labeled 1.3, and it's another one of those 1.6s. So we've got to get through 1.6 to be able to do that. So I'll hold off on that. Okay, so we'll see. We did that. Okay. So 1.6 to 1.8. Okay. We've actually sort of talked about, we've talked about some of this sort of roundabout, but anyway, formally defining some of this. A rule of inference consists of premises and a conclusion. Premises are one or more propositions given as true. I don't know if I'd formally defined that, but we talked about premises are sort of, they're things that you're given. Conclusion is a proposition whose truth follows logically from the premises. We also can say that sometimes a conclusion, we say that we're trying to prove the conclusion. I mean, that means that we're trying to show that it follows logically from the premises.
So a premise is something that is true?
Yeah, well, yeah, or something that is given to be true. They're sort of like accepted, things that you're accepting to be true, and from those you're going to try to, derive something else. Normally the conclusion. Maybe you're not given the conclusion, you're just given a bunch of premises, and you're trying to see what you can conclude from them, but...
And a conclusion is proposition.
Yeah, conclusion, well, it's... Assuming you get to a conclusion, that conclusion is a proposition whose truth follows logically from the premises. Normally we give you something and we say, prove this conclusion from the premises. We mean show that the truth follows logically from the premises. It's just what you're trying to show. Now, something following logically from the premises it formally means if you take all of them to get like anded together, they imply C, and that has to be a tautology. A lot of these definitions we can sort of throw out when we start working the problems. It's easier to work the problems than it is to understand some of the definitions. Let's see. So here is an example of a rule of inference. Okay? And I hate the way they wrote this, but this is the way they wrote it. I like to put the P up top, but anyway, doesn't matter. If you're given P implies Q and you're given P, then it follows that Q is true. Okay, remember, these are premises, so we are accepting that those are true. So if I'm given P and P implies Q, I can say that Q is true. And a lot of these sort of just make sense when you look at them. I mean, it makes sense. Oh, if I'm given P and P implies Q, then sure, yeah, Q's got to be true because, the only way that the implication is true is if P is true is if Q is true. There are...
So if P was true and P implies Q...
Right, then Q is true. Now, we go through like some explanations of how this works. So if we draw out the truth table, P and Q, we've got P implies Q. Remember we were given P and P implies Q. So these are the two columns that we're looking at. If we AND those together, does that imply Q? So we got the truth value of this, and then we've got P and P implies Q implies Q. The definition said that for the conclusion to follow logically, then the implication has to be a tautology. And that's just what that's showing here. All of those are true, so yeah, it follows.
So wait, how do you get P and P implies Q?
Well, you're given these two propositions, and the definition was when you're given these propositions, if you AND them all together, they must imply, and AND them all together implies the conclusion that has to be a tautology. That's just what that truth table is showing. So we're only given two, P1 and P2. So if we take P1 and P2 implies Q, it's saying that has to be a tautology. And that's what the truth table is showing.
Oh, so it's...
It is a little hard to follow, and the beauty of it is that you don't necessarily need to know that all the time. All you really need to know are the rules of inference. It's sort of like a table that we summarize later. And one of those rules of inference is if you are given P implies Q and P, then you can say that implies Q is true. So if we have a proof and we've got, I don't know, you derive P and you derive P implies Q, you can also say that Q is true. And we'll see that in a proof.
I'm sorry. Well, what about the top part? What does that imply?
We're at. Here?
C follows logically from the premise that P1 will...
So what it's saying is when, in our case here, let's just make it simpler since we've only got two. If I take P1 and P2 implies Q, and I put that in a truth table, C follows logically from that, or Q follows logically from that if this is a tautology, meaning it's always true. And in the truth table, so here's the premises ANDed together, okay? And then here is that implication that we're trying to show. It's saying if P1 and P2 implies C is a tautology, and it is, because it's always true, then C follows logically from the premises. In our case, the conclusion was Q. So based on that truth table, what we can say is we can say that if you are given P and P implies Q, that you can conclude that Q is true.
I think I'm starting to get it. So essentially, C is... C conclusion is
Correct.
the ending of P and Q.
The conclusion is what follows logically from what you were given. So based on these, we are concluding Q.
Oh, because P implies Q and P implies Q?
Right. That is a tautology based on this truth table. Since it is a tautology, we can say if we are given P and P implies Q, then we can conclude Q. It's much easier to see when we use them in a proof. This is sort of the theory behind it. Here's one. All right. So this is using what we just talked about. So we have if it rains, the dog gets wet. So we quantify P as it rains, Q as the dog gets wet. P implies Q would be if it rains, the dog gets wet. And this is how we would quantify that. But it's exactly what we saw before. Now, we would have to be given it's sort of stating that here without explicitly stating it in English. But we are since we are writing that these are the two premises, we are not only are we given if it rains, the dog gets wet, we are also being given that it rains, right? Because these are the premises. So it rains. If it rains, the dog gets wet. Therefore, the dog got wet. So we can conclude Q from that. Yeah, this is how normally I like to see this rule written. You can switch the order. The order.
Oh, by the way, another way to write the conclusion rule is all of n of p of n implies p. Wait, no, that's that. Wait, I'm thinking dumb.
Yeah, what it's saying is when you and all these things together implies C. When you put that in a truth table, it has to be a tautology. In that case, you can say that the conclusion does follow from the premises. Again, though, it's much easier to just learn the rules of inference that have already been proven. I mean, this is one of several. This is showing, so it's, P and Q are propositional variables, so the rule of inference holds for complex proposition of all types as long as of the form of the rule is met. This is sort of, when I talked about, P implies Q, it could be some bigger statement implies some other bigger statement. That's what they have here. So they've got some compound statement over here implies the biconditional of R and Q. Well, if you're given what's on the left-hand side, we're given S and R or T, then I can say, okay, well, I'm given that, I've got this. That must mean that the biconditional R and Q, or R with Q, is true. It fits that same form. The same form of P implies Q, and you're given P. We've learned this one before. Our rule of inference can't just have one premise. P implies Q, therefore not Q implies not P. That was the contrapositive that we talked about in 1.1 or 1.2. Now, every logical equivalence is two rules of inference. So, what do you have here? P implies Q is logically equivalent to not P or Q is both the rule of inference. Yeah, we talked about this before. So we said that P implies Q is equivalent to not P or Q. So if I have P implies Q, I can break that down into not P or Q. By that same token, if I have not P or Q, I can also translate that to P implies Q. We did that before. They go both ways. Now, a non-rule of inference is called a fallacy. So let's see. If it rains, the dog gets wet. The dog got wet, therefore it rained. Okay? So what they're saying is that this is not a rule of inference. This is a fallacy. This is if you're able to prove this from these two statements, you're doing something wrong because it's not true. Now, how do we prove invalidity? Well, we can construct a truth table, and then all we have to do is find values for P and Q that make the premises true and the conclusion false. Okay? So, in our case, let's see, P is, if it is raining. So, P and Q, we just list the values. P implies Q, we're just constructing basically the truth table for implication from these. All right. Then we've got Q and P implies Q. Just looking at these. And then we've got this is the thing that must be a tautology for it to be a rule of inference, or for the conclusion to follow from the premises. And that was Q and P implies Q. All of that implies P. And if you run through it, you'll find that in this case, when P is false and Q is true, the overall thing is false. So P false, Q true. So false, true, false. Yeah, that does not imply P. Again, a lot of these are obvious. You can look at the truth tables that they've constructed, but a lot of these are obvious. And we talked about this one when we talked about implication. So if it rains, the dog gets wet, right? Okay, so you're saying, okay, well, the dog got wet, it must have rained. Not necessarily. Somebody could have, I don't know, dumped a bucket of water on him or sprayed him with a hose. We talked about this when we talked about implication. Q is not it's not sufficient to satisfy this because he could have gotten wet in some other way. P could still be false even though Q is true. All right. So in-class exercise, verify that this is a fallacy. So let's see. So we've got P implies Q and not P, and we're trying to conclude not Q from that. So all you need to do is construct a truth table like this, where you've got values of P and Q, and then you've got columns for each premise, and then a column for the premises ANDed together implies the conclusion. And if it is a fallacy, then that last implication should have one or more that are false. If this is valid, then they should all be true. So take, 3 minutes to do that. This is more of an exercise in truth tables than anything else because, like I said, there's a bunch of rules of inference that we'll learn. We won't necessarily need to prove them because they are accepted as true. They've been proven before. All right, take 1 more minute. I started you off there. What other columns did you write?
Not P, not Q.
Not. Okay. This one would technically be. Oh no, I'm sorry. That is the conclusion. I was going to say that one would be optional, but yeah, we do. That is the conclusion. Okay. What else?
P implies Q.
P implies Q. Okay. Yep.
Not P and P implies Q.
Yep. Not P and P implies Q, or if you preferred, P implies Q and not P. Either one works. And then what is the last one?
Not P and P implies Q implies not Q.
All right, I put that in parentheses to make it clear. Okay, and then we just start filling them in. True, 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 false. False, true, false, false. Okay. Not P would be false, false, true, true. Not Q would be false, true, false, true. Okay. P implies Q. Does true imply true? Yes. Does true imply false? No. Remember, the only one that we're concerned with is this one over here. This is the one we said that all the premises anded together implies the conclusion. That has to be a tautology for it to be valid. Otherwise, it's a fallacy. So, we'll see. False implies true is true. False implies false is true. All right. Now, not P and P implies Q. False and true is false. False and anything is false. True and true is true. True and true is true. All right. And then finally, the last column. Again, if these are all true, then our conclusion follows from the premises. If they're not, then it's a fallacy. So not P and P implies Q implies not Q. False implies false. That's true. False implies true. That's false. Technically, we could stop there. We found one that's false. True implies... Wait, what did I do? False implies... I was looking at the wrong... False implies false. False implies true. That's true, sorry. Here we go. True implies false. That's false. True implies true is true. Okay, so I guess the question was to prove that this is a... To prove that this is a fallacy. Well, if it weren't a fallacy, it would be all of these would be true. And we found one that's false, so it's a fallacy. And namely, we found, the way that you would say it is, well, what I found when P is false and Q is true, the premises, which were Q, and P implies Q, okay, the premises are both true, but the conclusion, the conclusion is false.
Wouldn't the premises be not P, I thought?
What did I do? The premises were P implies Q. Oh, jeez. Not P. Yes. And really, all you, I mean, you can do this, or I mean, really, I mean, you can see it from here. The premises are true, but the conclusion is false. So the implication, of course, is going to be false. But anyway, since the implication was it wasn't all true, this is a fallacy. So what that is saying? Let's see. What was the conclusion? Not Q. Okay, what we are saying is that this is not sound logic. So this is not a rule that we can use. We can't use it because it doesn't work. Yes.
Oh, I almost finished with that because I was gonna check if this logic makes sense. I did it as a separate problem, so I want to make sure the logic makes sense.
What
Yeah,
you did the same problem?
I did a slightly different problem.
Okay, which problem did you do?
I think it was like the first one. It was P implies Q is P1. And P2 is P.
P.
Yeah. I was trying to find the conclusion.
Find the conclusion. Well, you would have to be. Well, the conclusion would be Q.
I got the conclusion is not P.
Not P.
Look at my logic.
Well, I mean, you're given that P is true. There's no way you're going to get to not P from there.
Oh, wait.
But this is exactly what we just did. We had some premises and we want to get a conclusion from it. We ran through that exercise, and if you did it with this one, you would get something similar. This would be a fallacy because I can look at that though and tell that it's not true.
Oh.
Definitely, you can't get not P because you're given that P is true.
Because I did.
Did you come up that it was a? So you got P implies Q and P. Okay. But you don't have a conclusion. Like you're starting with a conclusion that is like unknown.
Yeah.
What is your conclusion? Or where did you come up with the conclusion here?
I didn't do this.
I mean, so at some point you converted C to not, is that Q?
Yeah, that's Q.
Well, yeah, you still wouldn't be able to get that from there. So what do you, this is just, like where you said this was true, you said, what do you got there? You took these, you got P implies Q, and P implies
C.
not Q. And you said that was true. That was just an incorrect statement. I mean, you can't say that's true. You need to draw a truth table for that. And you would see if you drew a truth table,
No, I was trying to find a conclusion because I thought that
you would get one of the things that's false.
No, I thought that conclusions proposition to truth logically follows from the premise. So the conclusion, so this statement is always true. This statement. Or am I confused?
No, the statement is only true if the conclusion follows logically from the premises.
Yeah. Basically, these two premises, I ANDed them, and that implies the conclusion, correct?
Well, if it is logical reasoning, then the truth table for that would be a tautology.
And a tautology is truth.
Right, but in your case, the truth table would not be a tautology. We would end up with something like we have here, where one of the items is false. Maybe more. It could be more than one. It's just got to be at least one.
But how? Because I'm pretty sure I did this.
All right, well, let's do it. So you had Q. P implies Q.
No, I had P. P implies Q.
You had P.
Yeah.
Oh, I'm sorry. That's right. You had P. P implies Q. And from that, you wanted to derive
A conclusion.
of not P.
Yes.
Okay. So so you got that, and the conclusion was not P. Okay. So can I piggyback off of this other one? No, because I got to draw the columns. Okay, so P, Q. Not P. P implies Q. All right, and then you would need to AND these together. And then the last one would be P and P implies Q implies not P. Okay, so true, 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 false, false, true, false, false. All right, not P is false, false, true, true. P implies Q is true, false, true, true. P and P implies Q, true and true is true. True and false is false. False and true is false. False and true is false. And now, P and P implies Q implies not P. So the first one, true implies false. That's false. So that's going to be a fallacy. I mean, we can go through the other ones. False implies false is true. False implies anything is true. But yeah, the implication has one that's false, so that is a fallacy, meaning that it is not. This one is kind of obvious, though. I mean, you're given P. The universe would end if you could conclude not P from that. I mean, there's no way you could be given that P is true and then end up proving that it's not true.
I don't understand though. I did the logic right here.
Well, let's talk about that after class because we got to get through some of this. But yeah, we can look at that and I can. But what's here? This is the answer. I mean, one of the implications is false. So the entire logic is a fallacy.
Okay.
But again, as long as you know the ones that we are using, which is what's in this. Oh, switch the source. Which is what is in this table. There we go. I mean, these are the ones that you need to know. So the one that we just did the truth table for and showed, has a name called modus ponens. All right. Now we won't go through the exercise for all of these other ones, but here they are. So if I've got not Q and P implies Q, then I can conclude not P. That's called modus tollens. This is the one I think that we used before. Sean, you used this one, right?
Yeah.
Because it looks logical, right? And in fact, it is. If I've got P implies Q and I've got Q implies R, then I can say P implies R. And I could prove that by doing that exercise that we just did with the implication that we have there. But this has a name, hypothetical syllogism. This is the one that I don't know, this one always, is it, not this one. There's another, this is the one that always throws me. I always have to break down the implication for modus tollens to sort of convince myself that it's true. But if you think about it, what I've got here, if I break that down, I've got not P or Q. So if not P or Q has to be true, and I'm given that not Q is true, then not P has to be true. But anyway, if you learn it, you don't have to do that. Here's one. I don't know where they came up with the term syllogism, but this is a disjunctive syllogism. If I'm given P or Q, and I'm told that not P is true, then Q has to be true. Because if one of these, and again, a lot of these just make sense. If one of these has to be true, and that's the only way an or could be true, and I'm told that, well, P isn't, Q has to be. And it's, again, got a name, disjunctive syllogism. Some of these other ones are kind of weird, and we'll see some cases where we can use them. It may not always be obvious, but there's one called addition. Okay, if I'm given that P is true, P or Q is true, right? So if I'm given, I don't know, give me a proposition. The sun is shining, then the sun is shining or the sky is green. That's true, because one of them is true. I'm given that the sun is shining is true. Here's one called simplification. If I've got two or really more things anded together, I can take any individual one of those things and say that it's true. That's called simplification. Because if P and Q is true, P had to be true for that to be true. This one, again, some of these are obvious that you may not just know the name of them right away. If I'm given that P is true and I'm given that Q is true, well, P and Q must be true. And then finally, this is the one that, there was a version of the book somewhere, like I said, that this was in 1.3, but I had my thing mislabeled. This is the one that we were talking about on that one before, where we had to use resolution. If I'm given P or Q, and then I'm given not P or R, these sort of cancel each other out, so I can derive that Q or R is true. It makes sense if you think about it, because in one of these cases, the P could be true, but in the other one it would have to be false. So one of Q or R has to be true. Again, you don't have to go through and convince yourself that these are true. These are ones that we can accept as true. They have been proven. All right, and then I just basically went through the explanation on the next few slides of these things. The ones that we commonly use, modus ponens is a popular one. Modus tollens is a popular one. This is a proof. It just shows you that modus tollens can actually be derived from the modus ponens and contrapositive. Anybody taking physics yet? My physics teacher used to say they were going to give us all these formulas. Like, all you need is F equals ma. You can derive everything else from that. Okay, I guess it's true, but there's no way I was going to do that on a test. So, yeah, some of these things can be derived from each other. You're not going to be like tricked on the test or anything. It's probably better just to look at these and sort of like, convince yourself, yeah, all of these actually make sense. And I think all of these do. All of these actually do make sense if you think about them. And like I said, I'm not necessarily going to take off if you get the name wrong. Take your best guess at it. Some of them are kind of easy. Like I'm adding something here. That's got to be addition. I'm sort of simplifying the expression here. That's simplification. Again, I'm more concerned with you learning the rule itself than the actual name of it.
So we don't know the names for the test for conclusions?
I need you to write down the name. If it's the wrong name, I never take off for it. Unless, maybe if you make up a name, I might take something off for it. I've had people do that, like they invented the name of something. I mean, just I mean, write down what you think it is, and we'll be fine.
Modus squiggle.
Yeah.
20
Honestly, if I'm grading the test and I see modus, I'm probably going on. Yeah, because that's my thing. I get these things, I get them confused too. I get modus ponens and tollens confused, even though they look very different. It's just, when you're going through them. 9 times out of 10, you're using this one. Like I said, this one, I almost never recognize this form. I always have to break this down to not P or Q, and then I'm like, oh yeah, okay, I could have just used modus tollens.
Wait, can you go back up?
Oh yeah,
I'm sorry.
right there or higher.
Yeah, thank you.
Yeah, and this, you've got access to these notes if you want to write out or print out that table right there. That's all you'll need. So you would ask me before going about how many things you need to know. This is it. Those ones I pointed out, what did we say, 5 plus these. 1, 2, 3, 4, 5, 8, 13. It's a good number, right? But that's it. That's all. And like I said, again, how many do you actually need to learn? A lot of these are obvious. I mean, yeah, you need to have looked at them, but sitting there like cramming these into your head, I think it's easier just to sort of think about them logically. Like, you used this and didn't even know you were using it, right? I mean, it is. It's a logical flow of things. Trying to match them up with the names, you might want to do that, but. Okay, so this is what I did on that problem. This was resolution at the bottom. It says this is used in automatic logic provers. That was given to me. I don't know. I haven't written an automatic logic prover in a while. But yeah, if I've got something and Q or something or Q, and then the not of that or something else, these two kind of cancel each other out, and I'm left with either Q or R is true. We use this one a lot, actually. It comes out helpful. Let's see, what do we got here? They are, when I was going through the notes looking at this, I was like, maybe we could have used resolution without them knowing anything else. And then I realized to prove resolution, they used hypothetical syllogism. So I guess we couldn't have because we didn't go over that until today either. Again, a lot of these proofs in here are not... they may be good practice for you to look at. You don't necessarily have to be able to derive these things from one another. We'll do examples. And we've talked about this before. Some of this is sort of repeat, but a derivation, formally, a chain of logical implications beginning with a set of premises and ending with a conclusion. Each link in the chain is a true statement and is derived via a rule of inference from previously known true statements. Like I said before, we sort of did things where maybe one followed from the previous one. This is sort of a complete proof with everything that we've gone over now. So we are given some premises. Again, we just list them out and we say that they are premises. We write down what we're trying to conclude, and then we try to get to the conclusion from what we've been given. Now, order is important only insofar as later numbered statements must be derived from earlier numbered statements. I mean, it kind of makes sense. What that means is, item number 4, I mean, I can't reference 5. I mean, that would make no sense. I mean, when I'm doing this proof, I write down 1 through 3, and then I'm trying to come up with 4. 5 and 6 don't technically exist. So I need, whatever I'm going to do here, I need to use something that's already been given, or I've already derived. So I've got to use something from 1, 2, and 3. In this case, I combine 1 and 3. I'm like, oh, I've got P, and I've got P implies something else. That means that something else must be true. Why can I do that? Modus ponens. And again, I used 1, I used 3, and this is, so I write down what I'm using and then why I can say what I'm saying. So that's modus ponens. So now, the next one, I took the contrapositive of 4. I only used one statement, and that was 4. So I said 4, comma, contrapositive. That's why I can say that. Here, I use 2 and 5. Again, use modus ponens. I've got not R, Not R implies not Q, so I can say not Q, and that's what I was trying to conclude. Now, what a lot of people will do, for whatever reason, they will leave these off. Okay, and sometimes it's easy. So at number 4, you're like, well, you must have used one of them, or you must have used 2 of these, right? So, I might figure out that you were using 1 and 3. But when you get down here, looking back at these 5 statements, I may be able to go back through and find the answer, but often it is not clear if you just wrote not Q there, like, okay, well, why are you saying that? Or are you just like, well, I don't know what to do, so I'm writing down the conclusion. Always write down what numbers you used and what rule you used. And again, I think I mentioned this before. Normally when we write, when you write your final answer, if you had derived something that you didn't use or that didn't get you closer to the conclusion, I would just leave it. But if you're rewriting it, you could of course cross that out. But again, there's nothing wrong with with deriving things that do not necessarily get you closer to the conclusion. That's part of the derivation process a lot of times. Okay, when a derivation succeeds in proving the conclusion, it's called a valid argument. If a derivation is not a valid argument, then it is fallacious. To show that it's fallacious, all you have to do is find an assignment of truth values that make the premises true, but the conclusion false. That's exactly what we were doing when we were trying to prove these things in the first place. So suppose we were given the following, and we're trying to conclude Q. If we can just find one case of where the premises are true and the conclusion is false, then we know that we're not going to be able to conclude it. So we can say that that's fallacious right away. And in this case, I don't know. Let's just say they did it by inspection, by looking at it. But they found out, okay, well, if P is true, Q is false, and R is false. So that would make this true, true implies false implies true, true implies true. So all the premises are true, but Q is false. There's no way I'm going to get to the conclusion that Q is true. So I found a case where I made these true, but the conclusion false, so the whole line of reasoning is false. And like I said, normally when we're doing proofs in here, I want you to actually prove something. I'm not giving you something that you're going to go through this big long thing and find out that you can't get the conclusion from the premise. Okay, so let's see. Do I have because before we talk about, well, it's not really a trick, but let's do one of these. Okay, so I gotta have something to cover up the answer. This is one of those that said 1.3 and I changed it to 1.6. Okay. I always forget that you can't see it. Take about 2 minutes and try to do this one. If you got the notes in front of you, you can try to come up with the name of whatever you use. If not, that's okay. I'll write it down as we go. Let's see, what is it? 634. Do it at 636. seconds. Okay. So, who remembers the first step in any proof?
Write them down.
Right. Write down your givens. So that's what I'm going to do. And what we can do is we can use these later. Now, some people will, for whatever reason, that they will see immediately, oh, I can break down that implication. So they'll write down 1, P implies Q, and then they'll say step 2 is not P or Q. Nothing wrong with that. Just make sure that you label everything. So I'm going to label all these givens. As long as you label the givens, it's okay not to use a given until step 7, or whatever if you want to. Okay, and what we're trying to prove, our conclusion here is R. Okay, so, there's plenty of things we could do. What's the first thing somebody did?
I did the, I don't remember the rule, what it's called, but using 1 and 2, you know that Q or R is true, because if P is,
I think you tried to use resolution.
I think I did,
But yeah, that's with ORs.
Yeah, my bad.
But although I think we might get there. Let's do definition of implication. Not P or Q. Okay, that's one definition of implication. And then let's do the same thing to 2. P or R. 2 definition of implication. And then 6, you got Q or R,
Yep.
right? And that was 4, 5, and resolution. And I guess sort of inadvertently there we sort of came up with another rule of inference that isn't in the table. It appears that if you have P implies Q and not P implies R, then Q or R is true. Didn't know that, right? But we used what we knew to derive that. All right, so let's see. Oh, there's only one step left. Which statements can I use to finish this off? Well, first of all, my statement is going to be my conclusion. But what statements help me with that?
6 and 3.
6 and 3. Yes.
Modus and Linus, something like that.
Is that, let me cheat. Disjunctive syllogism.
Oh.
Wait, is that right? Like I said, one of the reasons I don't make you remember these names is because I don't remember them either.
I did a whole another way.
There's several ways.
First of all, I took number 1. I did the inverse, where it's not used.
Yep. And then we're done. We could say, well, I guess we don't even need to say QED there because that was the conclusion we're trying to get to. All right, what way did you do it?
Oh,
Here's how I did it in my answer.
well, I first took the inverse of 1, and then,
Do you mean the contrapositive?
yeah, contrapositive.
Okay, so you got not Q implies not P.
Let me rewrite that. And then I took 4, and then I took 4 and step 2, and I did a hypothetical.
So not Q implies R. Oh yeah, that works.
And then modus ponens.
And then modus ponens. Yep, that works too. Yep. Often there are several ways to get to the conclusion. When the conclusion is true, of course. Yeah. Any way that works is fine. Like I said, I've sort of gotten myself into a thing. Unless I see 2 implications that automatically go together, I start breaking them down. So if I saw P implied Q and Q implies R, I would probably write P implies R. But if I don't see one like that, I normally just start breaking the implications down. That normally reveals something that I might need. All right, so let's see. A couple more slides, we'll be done. I swear this thing is scrolling when I'm not looking at it. It goes back up. Okay. Trick. Not really a trick. I mean, maybe this is a trick. Some of the ones that they say are tricks aren't really tricks. Okay, and I think this is, no, that's where we're at. Okay, proving implications. So if we are trying to, if our conclusion, if what we're trying to prove is an implication, we can use sort of the makeup of the truth table of an implication to do a trick. And what that trick is we're given these two premises, and we're trying to prove P implies R. Now, obviously, it does. You know, we've got a rule that says that P implies R. But this is just to demonstrate. If what you're trying to prove is an implication, you can just use what's on the left-hand side of the implication and say that I'm using the implicational premise. And the reason that you can do that, well, is what's in the star there. We can use this because the implication is always true if P is false. So we don't care what happens when P is false. Let's see what happens when P is true. So we can basically just, that's what we're doing. We're saying, okay, P is true, implicational premise, because we don't care about the false cases. Because in the false cases, when P is false, we know that the implication is true. The only time that it can't be true is when P is true and R is false. So let's just sort of assume that P is true and see what happens. So it sort of gives us another given that we can use. So I say P, implicational premise. I can only do this when my conclusion has an implication in it. And from there I can do whatever. Okay, I can use 3 and 1 and modus ponens. I've got P implies Q, so I know that Q is true. Then I can use 2 and 4, Q implies R, so R is true. And then, so when you use the implicational premise, you use what's on the left as sort of like a given. Once you prove what's on the right-hand side, which is R, you sort of link it back up. Once you get to R, you're technically done. Put them back together. How can I say that? Well, I assumed P and I derived R. P implies R, implicational proof. That's the reasoning why we are done. I assumed P was true. I was able to arrive at R, so this implication must be true. Again, we're assuming it's true, and we get to R. We don't care what happens when it's false, because we know it's always true when it's false. Just something you can do. And then this one, we won't go over an example of this. This is kind of self-explanatory. If you're trying to prove P implies Q, you can also prove, or anything really, you can prove something that's logically equivalent. So if you're trying to prove P implies Q, it's perfectly fine to prove it's contrapositive, because we know that the contrapositive is logically equivalent to its counterpart. And I guess you could combine those. You could prove the you could prove something that's logically equivalent, and you could also use an implicational proof. All right, and again, I won't go through that. Let's see what we got. We got 2 minutes. Yeah, we'll stop there, and we'll pick this up tomorrow, because this is a little more in depth than I can do in 2 minutes.
Thank you.
Okay, everybody's here.
So tell me, why is my equations incorrect here?
Yeah, let me see your equations.
Right here.